So hi, welcome back. This is the third video of basics of antenna. We're going to talk about retarded potential. So what is retarded potential? Before starting retarded potential, we have to understand about retarded time and the meaning of it. So time varying potentials are called retarded potential. You might not have understood this like right away, but I'll make sure that you understand. So let's read the definition first and I'll give you an example. Time at the source when the signal actually started traveling to reach a certain point at the current moment. Time at the source. This is a very important thing. Time at the source when the signal actually started. Time at the source when the signal started traveling to reach a certain point at the current moment. So it's not the time. It's not the travel distance that I'm mentioning. It's about the effect being transferred, and it's not like after turning on the switch, when at the which moment you see. It's about when you turn on the switch. It's the time at the source. It's the time at the source and when it starts, the effect, the turning on of the effect starts traveling, and this time period that it takes is called the retarded time. So I think you might have been clear with it. So this is the formula for it. Time to retarded time, tr, is equals to current time at the source minus distance divided by c. You can mention it like the distance, like it's the speed, it's the velocity of the signal. So yeah, I've mentioned it here also. If it start traveling, it's not a travel time but the time at the source when effect begin. Like from the example, you can see you are here and the switch is here, and I just turn it on at like 1 microsecond, and this is the retarded time that we've calculated in the 10-meter distance, considering c is the speed of light. So okay, so now let's begin the retarded potential. What do you mean by retarded potential? Analogy. Let's keep one analogy and you don't understand. There's a voltage you feel now at your position. It's the voltage you feel now at your position caused by when the charge was in the past, not where it is now. So it's like, let's take an example. If I throw a ball at you, so this ball that I threw is because of the past. It's because of the past that you are currently realizing it at the present. So if I throw another ball, you will realize it in next step. Not suppose I'm here and you're here. So at 1 second I threw the ball at you, and at 2 seconds you receive the ball, and another second, at 3 seconds I also throw the ball, you will receive it at 4 seconds. So this time, due to this charge, you are experiencing certain okay, you're being hit on that head. So that similar concept, we can mention it on retardant potential. It's a voltage you feel now at your position caused by where the charge was in the past, not where it is now. So let's define it in a standard way. The retarded potential at a field point is the electric or magnetic potential produced by a charge or the current produced by charge or current, taking into account the finite time required for the effect to propagate from the source to the field point. The same thing that I mentioned. It's not about the heating, but now let's use the word electric or magnetic potential, and it's produced because of charge or current, and taking into consideration about the finite time that it's needed for propagation from the source to the field point. So derivation is very simple. You don't have to worry about it. So you can see this scalar electric potential formula. This you can find of what it is. So very easy. You can write del L dl upon 4 pi epsilon naught for scalar potential electric potential, and for vector magnetic potential it's mu I dl upon 4 pi epsilon naught. Again, let's revise. So v is equals to del L dl upon 4 pi epsilon naught r. For remembering, you can use 4 pi epsilon naught here and here as well, and you have dl on both. You have dl on both, and for scalar potential you can just write del L, and for magnetic potential you can write mu I. That's as simple as that. So yeah, I don't have to remove I don't have to explain del L, meaning it's linear charge density, and it's similar down as well. So it's without non-time varying. Until now we have never considered time varying factor in our syllables in most of our electromagnetic course, and lots of syllabus. But now when we see when we actually have time varying concept into consideration, we can actually use in this bracket, considering that this is time varying concept. Now del L, the linear charge density, and the current is time varying. So this is the simple derivation. So for using I in any kind of like future reference, we don't use I, we can use this formula, because I cos t, in this factor comes into role. Okay, so let's see, because it's on straight line, so we actually take I naught cos omega t. And since it's the retarded time, we have to subtract t dash, with meaning the retarded time. And from the above lecture, we know that t dash is equals to r by v, considering this is the retarded time. And we've just mentioned it, and it's very easier effect now, source in the past. So let's talk about what is polarization. When EM wave propagates, the electric and magnetic field components also change their magnitude, called polarization. As simple as that. When electromagnetic wave propagates, when electromagnetic wave is propagating, the electric and magnetic field components, the field components will also change their magnitude, called polarization. So that's it for this video.